Bismillahirrahmanirrahim. Today we are going to discuss a very latest technology which is very effective and useful, and its name is supercritical extraction technology, or it is also known as supercritical fluid technology. Actually, under the Federal Resources Conservation and Recovery Act, industries that use organic solvent must comply with strict regulations concerning on-site storage, recycling, disposal, and off-site waste transport. Together with the Federal Clean Air Act, these regulations are intended to suppress pollution that would occur through excessive solvent evaporation or improper disposal to contaminate soil and water resources. It would be an extremely attractive proposition to have media that would serve as a versatile solvent without carcinogenic properties or the potential for environmental degradation. Indeed, this goal has been brought to fruition with the advent of supercritical fluid technology or supercritical extraction technology. Across global research is being conducted to assess the efficacy of many emerging non-thermal technologies in food processes to minimize the deleterious effect of thermal conventional processes like pulsed electric field, ohmic heating, ultraviolet light, pulse light technology, ultrasound, cold plasma, high hydrostatic pressure, and ultra high pressure homogenization. Consumers crave for food with better nutritional qualities, coupled with food safety and use of green technology. The number of potential applications for supercritical fluid extraction continues to grow globally, which is verified through the increase in patents deposited in the last few years. The increase in the application of this technology in the industrial area is mainly due to selectivity, facility, and separation capacity that the technique allows in obtaining a great number of organic compounds, of which many are impossible or non-viable to extract through traditional processes, or those whose purification needs high resolution. The high utilization of organic solvents in the different industrial processes such as fat and oil extraction, obtaining bioactive functional compounds, removal of heavy metals, polymer processing, fuel production, among others, represent a globally discussed issue due to the harm caused to the environment. In the light of this picture, in 1987, the Montreal Protocol was introduced, and in 1997, the Kyoto Protocol, which had as its main objective to restrict or eliminate the production and utilization of solvents that cause harm to the ozone layer. The great interest of the scientific community and the industrial sector for supercritical fluid extraction technology is directly related to the restrictions to the use of organic solvents, both in the preparative processes of samples used in various industries and in a higher ecological consciousness in the use of different analysis methods involving extraction. The extraction technique most widely known as the supercritical fluid extraction since its inspection has been touted for its exceptional performance. Presently, the utilization of supercritical fluid extraction is extensively applied not only to the food and drug areas but also in the areas of toxicology, chemistry, environment, textiles, petrochemicals, polymers, and among others. Significant achievements in the area of supercritical fluid technology over the past 3 decades have pushed the extraction of natural plant material using this method for extraction and has been described as an environmentally safe technology. The natural sources could be plants, algae, microalgae, among others. Moreover, the goal of this technique is the high selectivity, short times of extraction, increased pollution prevention, and the use of non-toxic organic solvents. Supercritical fluid extraction is based on some properties of the fluids such as density, diffusivity, dielectric constant and viscosity and usually involves modification of some conditions such as pressure and temperature to attain a supercritical fluid. Under these conditions, a fluid is between gas and liquid because the density of a supercritical fluid is similar to that of a liquid and its viscosity is similar to that of a gas. In other words, we can say that supercritical fluids possess properties that are intermediate between liquids and gases. This unique phase is obtained through the exertion of pressures and temperature greater than the critical point. Near the critical point of a fluid, minute changes in pressure or temperature significantly alters the physiochemical properties of a supercritical fluid. This is especially important for synthetic application where reaction conditions, for example, the selectivities, rates and pathways are involved or multiple or complex pathways are involved especially, may be sensitively manipulated. Such reaction control is impossible using traditional organic based solvents. Further, due to the deleterious effect that many organic solvents have on environment and one's health, media such as halogenated carbons, for example, chloroform and dichloromethane, are being phased out of use and begin replacement are being developed. Supercritical carbon dioxide is an alternative and attractive since it is extremely inexpensive and poses no threat to the environment or human health. Thus, the supercritical state of a fluid is the state in which the liquid and the gas are identical from each other. In addition, supercritical fluids have better transport properties than liquids because it depends on its density, which unlike liquid solvent is adjustable by changing pressure and temperature. Now let's have a look at the terminologies used in the supercritical fluid technology or supercritical extraction technology. Number one is the supercritical. The term supercritical refers to a substance in a non-condensing and single-phase fluid which brought about its critical temperature represented by Tc and the critical pressure represented by Pc. Beyond this point, there is a supercritical region where the substance shows some typical physiochemical properties of gases or liquids such as high density, intermediate diffusivity and low viscosity and surface tension. Supercritical fluid. A fluid at a temperature and pressure conditions above its critical point is referred to as a supercritical fluid, which is a dense fluid with interesting properties in between those of a gas and a liquid. Its density is similar to that of a liquid, while its viscosity and diffusivity are similar to those of a gas. Therefore, a supercritical fluid can act as a solvent similar to a liquid but with enhanced mass transfer kinetics. On this account, use of carbon dioxide and water in the form of a supercritical fluid offers a substitute for an organic solvent. Supercritical fluids provide exciting opportunity to the scientists as they cater of various processing needs. They can be applied in a number of fields such as drug delivery, chromatography, synthesis, purification, etc. Now, here is extraction. Extraction is the contact equilibrium separation process where a solid material containing a solute of interest is brought into contact with a liquid solvent. Time is allowed for equilibrium to be reached and the target component to be transferred from the solid phase to the liquid phase, and finally the solid and liquid phases are separated by physical means. This also applies to liquid-liquid extraction. Principle of supercritical fluid extraction technology. The driving force for any extraction process is the solubility of the target compound in the static solvent, which depends on the interactions between the solvent and solute. Supercritical fluid extraction has emerged as a superior alternative technique for extraction of bioactive species from the natural producer because of its reduction of extraction time, less consumption of organic solvents, being suitable for thermosensitive substances, production of cleaner extracts, environmental dignity. Supercritical fluid extraction is based on the solvating properties of supercritical fluid, which can be obtained by employing pressure and temperature above the critical point of a compound, mixture, or element. By proper controlling of supercritical fluid extraction parameters, the extractability of a supercritical fluid can also be modified, which enable this process to find its field from food to pesticide research. Even though carbon dioxide is preferred extraction solvent for extracting non-polar compounds especially, the polarity of supercritical carbon dioxide can be increased by the addition of miscible polar compounds such as ethanol as a modifier. Due to the selectivity involved in supercritical fluid extraction process, the extract obtained by this technique possesses low concentration of undesirable compounds. Besides, supercritical carbon dioxide becomes gaseous after depressurization and can be easily eliminated from a flow system. Extraction parameter. The application of a supercritical fluid is directly related to its physico-chemical properties. The high density values combined with the pressure dependent solvent power provide high solubility and selectivity to the supercritical fluid. In addition, low viscosity values and intermediate values of diffusivity combined with the absence of surface tension of these fluids allow its rapid penetration into the cell and particles of the same sample matrix, extracting their interior materials. These characteristics facilitate the process of extraction and inactivation of vegetative cells. The parameters impact the efficiency of extraction, which is determined in terms of yield and recovery of the targeted component. Yield is the amount of total extract obtained per unit mass of the starting feed material, whereas the recovery is percentage of targeted component originally present in the feed material recovered in the extraction. Carbon dioxide as a supercritical fluid extraction. The extraction process using supercritical fluids is presently considered a feasible alternative for conventional extraction methods. The solvent in supercritical state show intermediate physical and chemical properties similar to that of liquid and gas, which increases the extracting power of the solvent. The high density of these fluids give them a high solvation power, whereas its high diffusion and low viscosity value provide a desired penetration power in the solid matrix. Selection of a supercritical fluid is very important for the development of a supercritical fluid extraction process, and a wide range of compounds can be used as a solvent in this technique. However, despite the fact there are many compounds that can be used as supercritical fluids, For example, ethylene, methane, nitrogen, xenon, or fluorocarbon. Most separating systems use carbon dioxide due to its safety and low cost. Among various supercritical fluids used for extraction, supercritical carbon dioxide is the most widely used since it is non-toxic, non-flammable, non-corrosive, and easy to handle, allows supercritical operation at a low pressure and near room temperature. Cheap and readily available in bulk quantities with a high degree of purity. Carbon dioxide has been described to ensure minimal alteration of bioactive compounds and to preserve these curative or functional properties. Supercritical carbon dioxide possesses the ability to solubilize lipophilic substances and can be easily removed from the final product. Another advantage is that in gaseous state, carbon dioxide at room temperature and pressure, which makes compound recovery very simple and provides solvent-free extract. In addition, the molecule is environmentally friendly and generally recognized as safe by United States Food and Drug Administration and European Food Safety Authority. The good understanding of the solubility behavior of the component of interest for food processing is supercritical carbon dioxide is essential. Solubility of a solute in supercritical carbon dioxide is highly dependent on temperature and pressure, which influence carbon dioxide density and subsequently solvent power. Increasing the pressure leads to liquid-like density of supercritical carbon dioxide, thus increasing the probability of interaction between solute and solvent, leading to a dramatic increase in solubility. On the other hand, the increasing temperature causes a decrease in supercritical carbon dioxide density while at the same temperature increasing the vapor pressure of the solute. The parameters impact the efficiency of extraction, which is determined in terms of yield and recovery of the targeted component. Yield is the amount of total extract obtained per unit mass of the starting feed material, whereas the recovery is percentage of targeted component originally present in the feed material recovered in the extraction. Co-solvents or modifiers include hexane, methanol, ethanol, isopropanol, and dichloromethane, among the others. However, ethanol is recommended as a co-solvent in supercritical fluid extraction because of its low toxicity and miscibility in carbon dioxide. Although its application is limited to its unfavorable properties with respect to the safety and environmental considerations. Other co-solvents used are nitrous oxide, similar in solvating and separation properties to carbon dioxide, alkanes, better solvent characteristics for non-polar solutes. This supercritical carbon dioxide technology utilizes pressure in combination with carbon dioxide to destroy microorganisms without affecting the nutritional content, organoleptic attributes, being a promising alternative for pasteurization of bioactive compounds in food and medicine, in which compounds would be destroyed by conventional thermal processes. Supercritical fluid oxidation. Supercritical water is now recognized for its capacity to destroy toxic or hazardous materials. Supercritical water is also an important medium for chemical synthesis. In this supercritical oxidation process, a solution containing the toxic and hazardous component is heated to near critical or supercritical conditions in the presence of appropriate oxidizer. Since the critical point of water is relatively high, 374 degrees Celsius temperature, about 374 degrees Celsius temperature, waste components can be burned to simple byproducts. Under the hydrothermal processing conditions, the main component of the waste are converted to three harmless byproducts, that is the carbon dioxide, nitrogen and water. By varying the temperature or pressure of the supercritical or near critical solution, significant control over the reaction can be obtained. Now the next is the supercritical fluid chromatography. One of the most successful application areas of the supercritical fluid technology and a commonly used analytical technique for the separation and analysis of drug molecules is a supercritical fluid chromatography technique. For drug analysis, supercritical fluid chromatography is useful when the solute can be dissolved in a supercritical fluid and has a high diffusion coefficient. Multiple gradients can be used in contrast to gas chromatography and high performance liquid chromatography. This high performance liquid chromatography is also known as HPLC. Various factors to be considered for supercritical fluid chromatography and proper selection of pressure, temperature, pressure reduction ratio, density or core solvent and solvent gradient is important for optimized separation and analysis. Now the next is the supercritical Friedel-Crafts alkylation. It is possible to overcome many of problems associated with conventional Friedel-Crafts reactions, both from an experimental point of view and a practical standpoint by using supercritical fluid technology, a heterogeneous catalyst and a continuous flow reactor. Advantages of a supercritical Friedel-Crafts alkylation are high product selectivity, easy product separation, clean technology, and longer catalyst lifetime. It is currently widely accepted that supercritical extraction technology is a green technology alternative to normal phase separation technology without most of its associated problems. In addition, moderately polar compounds can be separated by adding organic modifiers such as methanol, isopropanol, and acetonitrile. On the other hand, even if it is still on a manageable level, the use of this technology has steadily increased over the last few decades. Now let's have a quick review on the application of supercritical fluid extraction technology and where it is used. Number 1. Supercritical fluid extraction technology application in foods, pharmaceutical and fine chemical industries. Number 2. Decaffeinating of coffee and tea. Number 3, it is used in the extraction of essential oils such as vegetable and fish oils. Number 4, this technology is used in the extraction of flavors from natural resources. Number 5, supercritical fluid extraction technology is used in the extraction of ingredients from spices and red peppers. Number 6, it is used in the extraction of fat from food products. And finally, it is used in the fractionations of polymeric materials. Except these, there are all other advantages of this technology. Moreover, it is also used in the extraction of natural products. It is used in the photoresistant cleaning. It is also used as a Persian part of the cleaning materials and technology.